Hello, I'm Aleesa.
Hi, I'm Pavitra Kumar.
Hi, my name is Zikryl.
Hi, my name is Aida.
Hi, I'm Pian.
Hi, my name is Leia.
I'm Mirza.
Hi, my name is Aqiel.
Today our group will be discussing all about calculus.
That's right. We will also be briefly going over the basic concepts of calculus, differentiation, and integration, as well as how calculus can be applied in real life. We will also go through some problems involving calculus too.
Enjoy!
Calculus is a big term that gets thrown around a lot. But what exactly is calculus? Calculus is very different from the mathematics we have learned before. It is a field in mathematics that analyzes the calculation of instantaneous rates of change, curves, areas under curves, sequences, and series. Before the invention of calculus, all mathematics was static and it could only make perfect calculations of stationary objects. But as we all know, everything in the universe is always moving and changing. No object, from stars in space to subatomic particles or even cells in our body, is always at rest. Calculations have helped determine how particles, stars, and matter move and change in real time. Differential calculus and integral calculus are the two main parts of calculus.
One of the main roots that led to the discovery of calculus was the method of exhaustion that was used by Greek mathematicians. This is a method in which a polygon is used to fill the area of a complex shape. At the time, many used infinitesimals. Infinitesimals describe numbers that are close to zero but are not exactly zero. During the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz had expanded on the method of exhaustion and independently developed the theory of infinitesimal calculus. Isaac Newton had made this in order to aid in his investigation of physics and geometry.
Now, to understand what changes that we are dealing with in calculus, let me give you an example. There's a car traveling from point A to B. Its speed is 30 kilometers per hour and it takes 3 hours to reach point B. But in the real world, there's no way it would go 30 kilometers per hour for the whole journey. Due to traffic, it will have its fair share of acceleration and deceleration for the journey. And that, my friends, are the changes. If we see the journey as a graph, it won't be a steady line all the way, but a very beautiful curve with rises and falls. But in order to tackle the problem of changing quantities, calculus picks up three powerful tools. These tools are limits, derivatives, and integrals. Now there are many other things you learn in calculus, but these three main things are the most essential. Because of this, you will want to spend as much time understanding them as possible. Firstly, limits are the tools we use for precisely describing how a function approaches a value, and derivatives are the tools we use for describing how a function changes. And lastly, integrals gives us the area underneath the curve of a function.
One of the most fascinating aspects of calculus is how all these tools actually relate to each other. Although they may look completely different, the derivative is built from the limits and an integral can be thought as the inverse of the derivative. Using limits, derivatives, and integral calculus can solve a variety of problems, like where to sit in a theater for optimal viewing, or even how to make the perfect can for soft drinks. Now let's take a closer look at differentiation and integration.
As we mentioned before, differentiation and integration are the two major concepts of calculus, and they are very closely related to each other. In simple words, differentiation is a process of finding the derivative or rate of change of a function.
On the other hand, integration is a method of adding or summing up the parts to find the whole. In fact, the integration symbol looks like this, and is actually derived from the elongated letter S to stand for summa, meaning sum in Latin. It is a reverse process of differentiation. Unlike differentiation, where we obtain the derivative from a function, instead, we obtain the function from its derivative.
The derivative is used to find the rate of change, and this can also help us find the gradient of a curve, as well as help us find maximum and minimum points.
The integral is calculated to find the function when its derivatives are given, which will describe the area, displacement or volume in which due to a collection of small data cannot be measured singularly. These two concepts may still be extremely confusing, so let's take a look at a practical example so you can see what we mean. Now let's say that per day, there are exactly 5,000 new COVID cases, and this goes on for X days. Then, summing this up, we can find the total number of cases from day 1 to day X. Since per day there are 5,000 new cases, the total number of cases from day 1 to day X is simply 5,000x. This is integration. Hence, we can say that the integral of 5,000 is 5,000x, and it works the other way too. The derivative of 5,000x is 5,000. This proves the integrals and derivatives are opposites. While this may seem like a basic example since the number of new cases per day remains constant, the same thing applies for an increasing and decreasing rate too.
Now, let's see how differentiation works. But first, let's fully understand the idea of limits. A limit is the value that a function approaches as the input approaches some value. Here's an example. We want to find the limit of x plus 2 as x approaches 2. How can we find this? Well, it's rather simple. All we need to do is substitute x equals to 2, and we will obtain 4 as our answer. But how does this work? Well, as is approaching 2, this means that x approaches 1.9, 1.99, 1.999, and so on. But x is never equal to 2. But as we can see, as x gets closer and closer to the value of 2, the value of x plus 2 gets nearer and nearer to the value of 4. But it won't exceed 4. So in this situation, we can say that x plus 2 has a limit of 4 as x approaches 2. Now, while this may seem completely off topic to limits, stick around because they are actually closely related. Well, we know that the gradient of this straight line is rise over run, or in other words, the vertical length over the horizontal length from one point to the other. My question for you is, what is the gradient of this curve? Is this even possible to find? This is where differentiation helps us. Let me explain. The gradient of the curve is actually the derivative of fx, and different positions of the curve will have different steepnesses. For example, here, it is not that steep, but as we go towards the right, it is much more steeper here. So actually finding the gradient of a curve is impossible. But now let's focus on this point here. Point A. What is the gradient at this point? Is it also impossible? Well, let me ask you something. Is the earth flat or round? Of course it's round. But take a look at your surroundings. The ground seems flat, doesn't it? But why? Let's say this circle is the earth, and you are standing right here. As we zoom in closer, notice that the ground seems to be getting flatter and flatter, almost like a straight line. Now, if we draw a straight line at this point, we can see that the curved line is almost the same as the straight line. We call this straight line that passes through this point of the curve the tangent at that point. Thus, we have discovered that a curved line can be approximated by a straight line. This solves our problem. The slope of the curve at point A is equal to the tangent of the curve at that point, and we already know how to find the gradient of a straight line. But wait, how can we find the rise over run of this line? First, let's define another point on this curve as point B. Then, let's define the vertical distance between the 2 points as delta y, and the horizontal distance between the 2 points as delta x. Then we can say that the gradient of line AB is simply delta y over delta x. But how does this help us find the gradient of the tangent at point A? Aha! This is where limits come along. As delta x approaches 0, point B gets closer and closer to point A, until eventually line AB becomes the tangent to the curve at point A. So, we can conclude that the gradient of the tangent to the curve at point A is the limit of delta y over delta x as delta x approaches 0. Now that we understand the concept of differentiation, let's actually learn how to do it. The basic formula is if y equals to ax to the power of n, then dy dx equals to an x to the power of n minus 1. Let's see some examples. When y equals to 3, then dy dx is equal to dy dx 3x to the power of 0. Now let's apply the basic formula. We will obtain that this is equal to 3 times 0 times x to the power of 0 minus 1, which is equal to 0. Next, what is the derivative for x? Again, applying the basic formula, the derivative of 4x is simply 1 times 4 times x to the power of 1 minus 1 equals to 4. Let's take a look at one last example. What is the derivative of 3x to the power of 3 minus 6x to the power of 5? All we have to do is simply apply the basic formula for each term. Then we will get that this is equal to 3 times 3x to the power of 3 minus 1 minus 5 times 6x to the power of 5 minus 1 equals to 9x to the power of 2 minus 30x to the power of 4. Also, note that there are other useful rules that can help us differentiate too, such as the following.
Next, let's learn about integration. First, let's understand how it's possible for us to find the area under a curve by integration. Take a look at this area under the curve. We can divide this region into many small strips, where each strip has a height of y and a base of delta x. Thus, the area of each strip is y times delta x. Now let's say that we divided this area under the curve into n smaller strips. Then we can say that the area of the n strips is the summation of y times delta x. But how does this help us find the area under the curve? Well, as we divide the curve into more and more strips, our calculations become more and more accurate. So we want n to approach infinity. We find that as n approaches infinity, delta x, or the length of the base of each strip, approaches 0. Thus, we can say the area under the curve is equal to the limit of the summation of y times delta x, as delta x approaches 0. And this is defined as the integral of y dx. Now that we understand the concept of integration, let me tell you about the two types of integrals in math, indefinite integrals and definite integrals. Indefinite integrals are defined without upper and lower limits. It is represented like this. N is equal to fx plus c, where c is any constant and the function fx is called the integrand. Definite integrals are integrals that contain upper and lower limits. On a real line, x is restricted to a line. A definite integral is presented like this. And this is equal to fb minus fa. Definite integrals are used when you are trying to find the area under a curve, but from one specific point to another. Something like this. Now, let's learn the basic technique for integration. The integral of ax to the power of n dx is equal to ax to the power of n plus 1 divided by n plus 1 plus c, where n is an integer, n does not equal to negative 1, and a and c are constants. Let me demonstrate an example. Here, we are asked to find the integral of 2x to the power of 2 minus 3x plus 5 dx. Applying the basic technique, this is equal to 2x to the power of 2 plus 1 divided by 2 plus 1 minus 3x to the power of 1 plus 1 divided by 1 plus 1 plus 5x to the power of 1 divided by 1. And of course, we should not forget to plus c. Simplifying this, we get 2x to the power of 3 divided by 3 minus 3x to the power of 2 divided by 2 plus 5x plus c. And we're done. There are some other rules that can help us integrate too, such as the following.
Now, let's go to an example problem for differentiation. Here is the problem. The curve y equals to x cubed minus 12x plus 1 passes through the point M for 17 and has two turning points R to negative 15 and S. First part of this problem, we are asked to find the gradient of the curve at point M. Since we know that M is a point in the curve, we can start solving this question by differentiating the equation of the curve. By the previous basic formula mentioned, we know that dy over dx is equals to an x exponent n minus 1. So, dy over dx for this question will be 3 times x exponent 3 minus 1 times 12x exponent 1 minus 1 plus 0 times 1, which would be 3x squared minus 12. Then we can find the gradient by substituting the x coordinate of point M into the equation. So it will be 3 bracket 4 bracket exponent 2 minus 12. So it will be 3 times 16 minus 12, which will be 48 minus 12, and it will be 36. So now we know that the gradient of point M is 36. Next, for question B, we are asked to find the equation of normal to the curve at M. We know that the equation of normal is y equals to negative 1 over mx plus c. And from the above question, we know that the gradient, y coordinate and x coordinate of point M. Then c can just be found by substituting in these values. At the y place would be 17, at the m place would be 36, and at the x would be 4. So it will be 17 equals to negative 1 over 36 times with 4 plus with c. And c will be 17 plus 1 over 9, and it will be 17 1 over 9. So the equation of normal would be y equals to negative 1 over 36 plus 17 1 over 9. Finally, for the last question, we have to find the coordinate of S and determine whether S is the maximum or the minimum point. We know that S is one of the turning point, so we can use the formula dy over dx equals to 0 to find the turning point. We know that dy over dx is 3x squared minus 12, so it will be 3x squared minus 12 equals to 0. And when we use the quadratic factoring formula, we will get that x equals to negative 2 or x equals to 2. Since the x coordinate of R is 2, so the x coordinate of S would be negative 2. Now we can find the y coordinate of S by substituting the x into the equation of curve. So it will be y equals to negative 2 cube minus 2 times negative 2 plus with 1. So we get negative 8 minus 24 plus 1, which we will get 17. Thus S is equals to negative 2, 17. Now we need to determine if it is a maximum or a minimum turning point. We can do this by using the nature table of dy over dx. So on the first row of the table, we will write the value of x, which would be x minus 1, x and x plus 1. So it will be negative 3 for the first column, negative 2 for the second column, and negative 1 for the third column. For the second row, we will substitute those x value into the dy over dx equation. So the value of dy over dx for the first column would be 15, second column would be 0, and the third column would be negative 9. Now we can sketch the tangents by using the sign of the dy over dx, which will be positive or negative. Now the first column, we know it's a positive 15. So the tangent would be in ascending order. And the second column, we know it's just a 0. So it won't be ascending or descending, it's just be a straight line. And for the third column, we know it's a negative 9. So it will be in a descending order. Now if we sketch this curve, we will get in an upside down U shape. This proves that it's a maximum turning point. Now we can conclude that the coordinate of S is negative 2, 17, and it is the maximum turning point. And below we can see the graph of the curve, which will show that S is the maximum turning point and R is the minimum turning point.
Next, let's go through a problem that relates to integration. Here's the question. In the diagram, the straight line x over 2 plus y over 4 equals 1 is the tangent to the curve y equals 3 minus x squared at the point A. For the first part of this question, we're asked to find the values of h and k, which are the coordinates of point A. Since point A is the intersection point between the straight line x over 2 plus y over 4 equals 1 and the curve y equals 3 minus x squared, we can find the values of h and k by solving this pair of simultaneous equations. From the equation of the straight line x over 2 plus y over 4 equals 1, subtracting x over 2 and multiplying by 4 on both sides, this gives us y equals 4 minus 2x. Therefore, 4 minus 2x equals 3 minus x squared. Then, subtracting 3 and adding x squared to both sides, we get a quadratic equation. X squared minus 2x plus 1 equals 0. We can then factorize this to get that x minus 1 squared equals 0, so x minus 1 equals 0, and hence x equals 1. Then, to solve for the y coordinate of point A, we can substitute x equals 1 into any one of the equations. Substituting x equals 1 into the equation of the curve, we find that y equals 2. Thus, the coordinates of point A is 1, 2. So we can conclude that h equals 1 and k equals 2. Before we move on, let's first find the y-intercepts of the straight line x over 2 plus y over 4 equals 1 and the curve y equals 3 minus x squared to make our work easier later on. We do this by setting x equals 0 and we'll find that the y-intercepts are 4 and 3 respectively. Now let's move on to question B. We're asked to find the area of the shaded region. We can do this by finding the area of this trapezium and subtracting it with this area under the curve, which is simply the integral from 0 to 1 of 3 minus x squared dx. First, we need to find the area of this trapezium. To find the area of a trapezium, we multiply the sum of its bases by its height and divide this value by 2. So in our case, the area of the trapezium is simply 4 plus 2 times 1 divided by 2, and the result is 3 units squared. Next, we can find the area under this part of the curve, which is the integral from 0 to 1 of 3 minus x squared dx. By applying the basic technique of integration, this is the same as 3x minus x to the power of 3 over 3 from 0 to 1. Then we substitute x equals 1 and subtract this with when we substitute x equals 0. Simplifying this, we will obtain 2 over 3 units squared. Finally, going back to the original question, we have that the shaded area is 3 units squared minus 2 over 3 units squared, which is equal to 1 over 3 units squared. Finally, the last question asks us to find the volume of revolution in terms of pi when the region bounded by the curve y-axis and straight line y equals k, which is this green area right here, is rotated through 360 degrees about the y-axis. The formula for this is pi times the integral from a to b of x squared dy. This formula is derived similarly to what we explained before, in which we divide the region under the curve into infinitesimal strips. Now from the equation of the curve y equals 3 minus x squared equals 3 minus y. So we can substitute this in, along with the values of our upper limit and lower limit. Then, integrating this will be equal to pi times 3y minus y squared over 2 from 2 to 3. After that, we substitute y equals 3 and subtract this with when y equals 2 to find the value of 3y minus y squared over 2 from 2 to 3. Simplifying this, our answer is 1 over 2 pi units cubed.
Cool, so we have learned quite a bit of calculus, but I don't see how learning all this can help us at all, other than getting good grades in MS, I guess.
Well, actually, calculus can be applied in a lot of ways in real life. Some of the concepts that use calculus include motion, electricity, thermodynamics, light, and astronomy. It may sound surprising, but calculus is also used in geography, computer vision, artificial intelligence, robotics, video games, and even movies. In addition to that, calculus can also be used to calculate the rates of radioactive decay in chemistry and even to predict birth and death rates, as well as in the study of gravity and planetary motion, fluid flow, ship design, geometric curves, and bridge engineering.
Statisticians also use calculus to evaluate survey data to help develop business plan for different companies. Because a survey involves many different questions with a range of possible answers, calculus allows a more accurate prediction for the appropriate action.
And an operation research analyst will use calculus when observing different processes at a manufacturing corporation. By considering the value of different variables, they can help a company improve operating efficiency, increase in production, and raise profits.
So in short, calculus can be applied in a wide range of occupation, notably architecture, engineering, design, and many more.
Wow, tell me more.
Well, let me tell you how differentiation can help us solve many types of real-world problems. Differentiation deals with the rate of change and issues in many sectors of the work field, including biology, chemistry, economics, physics, environmental science, and are met in many engineering and science problems, especially when modeling the behavior of moving objects. We can also use the derivative to determine the maximum and minimum values of particular functions. Now, I'm going to show you a real-life example to show that differentiation can be very helpful. Let's say we want to manufacture pens. So in our mind we think, how can we optimize our profits? And as we know, profit is equal to the selling price minus the cost price. And the cost price can be divided into two, which is fixed cost and labor cost. Fixed costs are those that will be included every month, such as electricity and water. So if we need to figure out the profit, we need to figure out the quantity to manufacture where profit is optimized. Let's assume the quantity of pens to manufacture where profit is at the maximum is equal to X. So let's say that the fixed cost is equal to X to the power of 2, the labor cost is 10X, and we decide to sell the pens at 20X. So from there, we can conclude that profit is equal to selling price minus cost price, which is equal to 20X minus in bracket X to the power of 2 plus 10X. Then we get 10x minus x to the power of 2 through simplification. And since we need to find the value of x in which the profit is at a maximum, I'm going to differentiate the profit. Then, by the basic formula, the derivative of ax to the power of n is n ax to the power of n minus 1. So, we will get that this is equal to, in the bracket 1, 10x to the power of 1 minus 1 minus 2x to the power of 2 minus 1. Simplifying this, we get 10 minus 2x. Then, since we are trying to find its maximum point, I will make it equal to 0, which will give us that dy dx is equal to 10 minus 2x equals to 0. Therefore, from here, we can say that profit is at the maximum when x is equal to 5. As you can see, differentiation is very useful.
Next, let's discuss how integration can be applied in real life. Integration is basically used to find the areas of the two-dimensional region and computing volume of three-dimensional object. How can this be applied in real life? One example is an architect or engineer who may use integration in determining the amount of the necessary material to construct curve-shaped construction, for example, a dome over a sports arena, and also to measure the weight of that structure. Integration can be used to improve an architecture not only of building but also of important infrastructure such as bridge. In electrical engineering, integration is used to determine the exact length of power cable needed to connect two substations which are miles away from each other. Specialized engineers frequently use integration as well when planning for long mission. To launch an exploratory probe, they must consider the different orbiting velocity of the Earth and the planet the probe is targeted for, as well as other gravitational influences like the Sun and the Moon. Integration is very much needed in physics too. For example, to calculate the center of mass, center of gravity, and the mass moment of inertia of a sports utility vehicle. Other example of integration uses is integration is used to calculate the velocity and trajectory of an object, predict the position of planet, and understand electromagnetism.
In conclusion, calculus is an extremely fascinating branch of mathematics.
Although it may seem very complex at first, it is not that difficult to understand and can be very useful.
We hope you enjoyed it and learned something new.
That's all from us today. I hope you enjoy watching the video and have a great day. Goodbye.
Thanks for watching. Bye.
Thank you. Bye.
Thank you.
Thank you and goodbye.
Bye.
Peace.